Okay, sit down, please. All right, quiet, please. Okay. All right. So all right. So today's plan, all right, is we'll look at flow measurement devices that rely on the Bernoulli. All right. So this is the last lecture on the Bernoulli equation. All right. So flow measurement devices. I think we look at pitot-static tube. All right. Venturi. Orifice plate. Okay. Those are the three. All right. There's also a subset there one. I think more like they call a vein or something like that. All right. With these three, there's this thing called the discharge coefficient, which I'll talk about. And actually, these two, all right, these two, yeah. Venturi tube, Venturi, tube. Okay. With these two, we also look at how we use them in the lab. So I tell you how to do it. Rather than have to repeat it again later, I'll tell you how to do the lab report. I'll do it all together in one go. Okay. And finally, we'll talk about energy. If got time, if not, I might do next time. Energy grade, line, and hydraulic grade line. Okay. All right. So that's the plan today. Save. Okay. So let's recall. Bernoulli equation looks like P plus half rho V squared plus rho GH equals constant on streamline. Alright, assuming steady state, no losses, no friction losses, no irrotational flow, and so on and so forth. Okay, in a very idealized case, no energy losses are basically, alright, no energy converting to heat and other things. Okay. What are you doing? Oh yes, okay. Okay, so, and I think earlier I mentioned this is the dynamic head or dynamic pressure. Since it's all in terms of pressure, this is the dynamic pressure. These two, all right, would be the static components. All right, they are not caused by anything moving, basically. All right. Okay. So one way of measuring velocity is to measure this pressure relative to these other two. All right. To measure this pressure. Okay. It's pressure, isn't it? All right. They're all in terms of, if you all the units are pressure. Okay. So if you write in terms of head, P on rho G plus V squared on 2G plus H equals constant along a streamline, then this one will become your dynamic head, and this one your static head. Okay. All right. One way of doing that is to measure the pressure at a stagnation point. All right. So here, measure pressure at stagnation point. All right. So if, let's say, in this case, normally you the static parts, the pressure, the H, and all that, you can measure quite easily. All right. In this case, for example, if you wanted to measure the velocity of a flow, all right, can you stick a probe in, a simple probe, and measure the velocity? And this is one way. Okay, this is a simple way. There are other more fancy ways, but this one is a very simple and direct way. Okay. So we need to. So initially the streamlines are all going nicely like this. All right, undisturbed. All right. Yeah. Stagnation point. Okay, so this is at pressure infinity, velocity infinity, some height lah. Alright, doesn't matter. Okay, so it's a free stream pressure, some wind or whatever blowing past you. Alright, to create a stagnation point, alright, simple one is we put this one is called a pitot static tube. Alright, this is traditionally the simplest way of measuring velocity. Okay, so the tube has an opening here. Okay, and this goes. Alright, and here maybe you can connect it to a pressure gauge, but in this case I'll connect it to a what do you call it? A manometer. Alright, but you can connect to pressure gauge or any other pressure transducer, anything that measures pressure. Okay, so here, alright, once there's manometer fluid in here, okay, so once the pressure increases inside, initially there could be some flow going in, but once the pressure inside here is high, alright, it will stop the flow from going in. Okay, not right? So the high pressure at that opening of the tube will stop the flow from coming in. Okay, not? So at this point 1, all right, can I say the velocity at 1 is 0? Okay, not? Huh? Because there's enough pressure inside the manometer tube, all right, to stop the flow from going in. Okay, all right. If there's not enough, then the manometer fluid will blow out. Okay, so if you don't fill up in case you don't do it properly, you don't fill up enough manometer fluid in here, all right, you actually shoot out here. Okay, like a fountain. Okay, so assume you did your work right, nothing of that happened. Okay, there's enough manometer fluid in here to stop that pressure from. Alright, so here the high pressure, you see that's why the fluid goes down. Okay, to push the fluid down. So here the pressure is higher. Okay, and the velocity 0. That's like a artificial stagnation point created by that tube. Alright, so normally this tube has two sides. You need to also measure the other component of pressure at that point. So we measure here. Okay. So normally this one is connected here. Okay, so the tube looks something like this. Maybe I shouldn't draw this here. Okay. No, it should be higher. Okay, not. All right. There are openings. There are openings here. Okay. All right. So at point 2, the velocity is still at the free stream velocity. It's not been slowed down. It's just at the side of the tube. All right. So the pressure here is P infinity. All right. And H1 is approximately H2. They are very close together. All right. Some not clear the concept. So this is a sample of pedostatic tube. All right. On this one. Yeah. Okay. Copy this picture down now. Yeah. No, see later. Right. Okay. Okay. All right. So this inside this metal piece here, there's 2 concentric tubes. All right. The inner tube has a hole here. You can see here. Focus. Yes, focus. There. You see or not? Yeah. All right. So there's a hole there. So the flow come in. All right. It won't go inside the tube because here connected to pressure gauge or something. It won't let the air flow through. Okay. To measure the pressure. So the inner, this hole is now that you just saw. Okay. You go in the inner. These are 2 concentric pipes. On the inner pipe, connect to here. All right. Here you will connect your. Here you will connect. The manometer will connect to these 2 ends. Okay. On the outer tube, all right, you can see here. You see the holes there? Okay. All right. Those holes, all right, on the outer tube will connect to the openings to the outer of the concentric cylinder, the tubes. Okay, now. All right, and they will run along and come out here. This one, you all can see it. Okay. So that's how a pedostatic tube arrangement is. So tube here, connect to here, openings on the side, connect to here. Okay or not? Alright. I'll bring it to the tutorial so I can see during the tutorial. If you want to have a closer look. Yeah, today, tomorrow, Wednesday got tutorial, 10 1 or 1, whichever one you like. 4 to 7. Fluid mechanics like. Alright, except for the normal Wednesday 1 to 4, 1 will be in the normal classroom. Yes, got please. Okay. Now you understand how that works now. So this device, okay, what we do is we can measure the height here, h. All right. We assume every streamline here is p infinity, v infinity. Here is p infinity, v infinity. Okay. So from point 2, we are measuring the p infinity. Okay, and the v infinity, because we don't stop that one, we just let it slide past. All right. So at point 1, okay. All right. So can we say P2 equals to P infinity? Okay or not? We didn't stop the flow. We just let it slide past the manometer. That's the manometer. All right. We just let it slide past. All right. It's not. You saw the holes at the side. Okay. Okay or not? Anybody disagree with this one? Okay, huh? All right. So, and if we apply Bernoulli along this streamline, we'll get P infinity plus half rho v squared plus h, all right, equals to, at this point, P1 plus, there's no velocity, half this v infinity squared, half rho, this one is 0 squared plus h. Okay, this h and this h same, so cancel. All right. So can we say P1 minus P infinity is equal to half rho v infinity squared. All right. So v infinity is equal to, this one multiplied by 2 P1 minus P infinity times rho. 2 divided by rho. Rho of, this one is the air. Assuming this is the air part. Normally this is used in the air, but it could be used in other fluid. Alright? Square root. Is that alright? And normally, if this was a manometer, then this will be equal to 2 rho manometer G H. That's the pressure difference on rho air. Square root. Alright? Because this what this is the manometer fluid, a rho manometer. Okay? Is that alright? Okay or not? Have you seen this? Have you seen this device before? Huh? When you see aeroplane, you don't see anything sticking out the front there. Some say yes, some say no. Let's see. Maybe you look on the internet, see whether got pictures shown or not. Alright. Okay, these are the normal ones. So on small aeroplanes, they normally got alright. This is good for measuring wind speed. Okay. That's the front opening. There may be a side opening somewhere here. Okay. Aeroplane. Another aeroplane one. Okay. In big commercial aircrafts, you can see them if you go to the airport before you board the plane with the nose of the aircraft facing you. It's normally below the pilot window. There's normally 2 or 3 tubes. Okay, they're normally the case. Big commercial aircraft, you wouldn't only rely on one in case nice big ones also got. Okay, all right. There are lots. I didn't see any from commercial aircraft ones. Okay, all right. There are lots. Okay, this is the example. Okay. Okay. So this one small aircraft, big commercial aircraft. Yeah, this one got. normally located near the front, where below the pilot window around here. Alright? That one let you to go and look for yourself. Maybe semester break or after the semester holiday, go take a flight somewhere. Okay? Okay. Alright. For this type of formula, okay, well, it may be nice to be able to memorize it, but be sure you know how to work it out, right, in case, alright? You need to. Alright, don't just apply formula only. Alright? Things might change around a little bit, then you might need to apply, you may need to work it out. Okay? Alright. Any questions so far? Okay, so this is the simplest one. Alright? Just this simple device, create a stagnation point, measure the pressure. Alright? The pressure difference between the stagnation point and the free stream, that is your velocity. And it's normally quite accurate. No need too much correction factor or anything like that. Normally quite accurate. Alright? As long as your estimate of this rho air is accurate. Okay? Because rho air tends to change depending on altitude and so on, and temperature and all that. The density of air changes a lot. So there could be some problem there. Alright? So as long as your density of the air or the gas that you're measuring is known accurately, then you're okay. If not, then a bit the error. Okay. Any questions so far? Alright. So the next devices, a bit more complicated. Alright. Also measuring pressure. Okay. We call this a Venturi tube. You saw this in the lab, isn't it? Alright. Okay, so a Venturi tube is basically a gradual contraction. Alright? And then after that it expands back. Alright? So it's a tube with a gradual contraction. I only draw a 2D view of it, but it's actually a tube. And this part is a bit like a cone, conical. Okay? This part is also another tube. So there's a gradual contraction into a small tube, then bigger into a bigger tube. Okay or not? Right? Like exactly like in your lab, isn't it? Right? You saw? Okay? Okay? So we normally measure the pressure here and the pressure here. Alright? And we put that into a manometer. Okay? Alright? You expect here the pressure higher? You expect here the pressure higher or here the pressure higher? Here, isn't it? So if the manometer fluid is heavier than this one, it will tend to drive this down. Okay? Okay? Something like that. Okay? And this will be the H. Alright? Okay, so we call this point 1 and we call this point 2. Alright, and this is our control volume. Here we need to do both. So this is our streamline, not steady as well. This is our streamline, okay, and this is our control volume. Draw outside lah, draw outside. Okay. Alright. So we don't know V1, we don't know V2. Normally we don't have. We know V1, we know V2 already because we don't know V1, we don't know V2. We know H1 normally is about H2. It's normally horizontal tube. P1, we do know P1 minus P2 is equal to rho GH. Alright? here, okay, I'll let you work it out. Normally, if you have manometer fluid on one side, all right, because remember, the pressure here and here is the same, correct or not? All right. So you work it out between when you go here to here, here to here, and when you go here to the equivalent point and up to here, the difference in pressure is rho manometer minus rho the other fluid. I don't know, rho. All right. GH. Okay. Other fluid. Is that okay or not? Can believe or not? All right. Those can't believe, I'll show you lah. All right. Okay. So maybe let's call this height X. Right? It makes no difference now. Later X will disappear. All right. For those who don't believe this one, I show you. Okay. How to show you? Okay. So this point I call this P naught. Say. All right. On this side, P naught minus P1 is equal to rho other fluid G H plus X. Is that okay? Or not? Yes or no? H is this distance from here to the top of the manometer fluid on one side, and from here, from the top of the manometer fluid to the 2.1 and 2 is distance X. Maybe I'll stop calling it other fluid. You might see, I call it just rho 2. Alright? Is this okay or not so far? Alright? And if I do it on this side, I'll get P naught minus P2 is equal to rho manometer GH plus rho 2 GX. Okay? And I subtract the 2, I'll get, this one subtract 2, this one's 1, 2 subtract 1, I'll get P1 minus P2 is equal to rho GX cancel out, rho M minus rho 2GH. Is that okay or not? Alright? Is that okay or not? Alright? So, I put a pedostatic tube, I measure the pressure, but in your experiment, use pedostatic tube, but it could also be done using pressure gauge, pressure transducer, and other types of equipment to measure pressure. Alright? But in your case, you did using a manometer. Alright? Now comes the interesting part. Alright? We want to find out, we measure the pressure, so P1 minus P2 we know. We want to work out what the velocity and what the flow rate is. That's the whole point of putting this device there. Not just to measure pressure. Okay? Measure pressure is a means to get to the end, which is to get the flow rate. Okay? Okay? So to get the flow rate, first, there's two unknowns, V1 and V2. I need two equations. One equation will be the, what? Bernoulli. The other equation? What do you think you know? No forces, what? Momentum. Alright, the mass flow, the conservation of mass. Okay, so two equations, two unknowns, so we should be able to solve. First equation, m dot in equals to m dot out. Alright, rho A1 V1 is equal to rho A2 V2. Alright, this is rho 2, rho of the fluid inside. Okay, which can cancel out. You will get V1 over V2 is equal to A2 over A1, which is equal to pi D2 squared over 4 divided by pi D1 squared over 4, which is equal to D2 squared over D1 squared. Is that right? Okay or not? So just in area, instead of in terms of area, in terms of diameter. Okay, diameter we do know. Okay so far? So that's the first equation, V1 over V2. Second equation is Bernoulli. P1 plus half rho V1 squared plus rho GH1 is equal to P2 plus half rho V2 squared plus rho GH2. So you cancel out because the same height. Okay? So what can we do now? We can rearrange so that, okay, we can rearrange. How to rearrange? Okay, move here. P1 minus P2 equals to half rho V1 squared minus V2 squared. It should be V2, P1. Is that okay? Alright? Okay or not? So I move the P2 over this side, move V1 over this side. You get to this. All agree? Okay? Then this one depends. You want in terms of V1 or in terms of V2? That's why in terms of V1. V1 is the main part. So V2 is equal to D1 squared over D2 squared V1. Okay? Alright, so put this one in here is equal to half rho square this whole thing. D1 to the 4 over D2 to the 4 V2 squared minus V1 V1 squared minus V1 squared. Is that okay? So V2 squared replace with square of this thing here. Is that okay? Alright. So now rearrange, we get equals to V1 squared half rho D1 to the 4 over D2 to the 4 minus 1. Right? So V1 is equal to P1 minus P2 over half rho D1 to the 4 over D2 to the 4 minus 1. And the whole thing square root. Okay or not? Alright? And if you had, alright, V1 is equal to this rho, this should be rho 2 actually. I forgot all the rho 2. After a while I select off. Okay, this all should be rho 2. It's the rho of the fluid inside the pipe. Okay, so Alright? So if we measure the pressure P1 minus P2, we can get out what V1 is. Alright? And if you want V2, alright, you can just multiply this whole thing with D1 over D2 if you want, but normally it's not here. Okay? You can Q, alright, which is equal to V dot, volumetric flow rate of 1 is equal to V1 times area, which is equal to, what is it? Velocity times area. Alright, so pi D1 squared over 4, alright, multiply by P1 minus P2 over half rho 2 P1 to the 4 over P2 to the 4 minus 1. Is that okay? Alright? Again, Q is volumetric flow rate. Alright? And you want m dot, you just multiply that with rho. Alright? M dot is equal to rho Q is equal to rho multiplied by this thing. Rho multiplied by pi D1 squared over 4 square root. Okay? Is that alright? Don't memorize this one, alright? If the problem in the exam or the require you to work it out, it's best you be able to work it out. Alright? You can try and memorize it, but what they'll do is they'll twist something there and then your formula might need something to adjust. Alright, so be clear how this was done. Alright? So we started with the continuity equation, with the manometer equation, the continuity equation, and the Bernoulli equation, and then based on the pressure measurement here, once we measure the pressure, we can work out what the flow rate is. Alright? Okay? So, any questions so far? Alright. Okay. So, this one was for Venturi tube. Actually, orifice plate okay. Normally you measure the pressure just before the plate and just after the plate. Alright? Flow going this way. Alright? So the flow would squeeze into this hole. Alright? And then further out, it will expand out later. Okay? So, you all know what orifice plate is, isn't it? Alright? It's just the two flanges of the pipe. You put a plate in between, and the plate has a smaller diameter, D2. Alright? So this is an alternate arrangement. Why you do like this? Huh? Why you do? Huh? Okay? Normally the reason why you do like this is because this one a lot cheaper. A lot easier to make. Right? Two flange, you stick a plate inside. The other one, you have to make the cone shape, the gradual, make a smaller pipe, then gradually expand back again. More expensive. Alright? Especially if it's a big pipe, a lot of welding to do, not easy to shape that conical shape and all that. Alright? Okay, so this one is a lot cheaper. Okay? Principle is also the same. Okay? You are constricting the flow to a smaller diameter. Okay? If here is P1, here is P2. Do you expect the analysis to be the same or not? Alright? If this pipe not very clear, I'll draw a bigger one. Okay? Do you expect the analysis is same or not same? Same. Okay? This is a pipe. Alright, we have a plate here. This diameter here, D1. This diameter further down, D2. Okay? Alright, so here, essentially the streamline is supposed to go like this. Alright? So before that, it was like the main pipe. And then after that, if you measure close enough to the hole, that's why it's important to measure close to the hole. It's as if you are measuring in the small pipe, the pressure in the small pipe. Alright or not? Okay? Before it expands out again. Okay? So, and then here is P2 and so forth. Here is V2, here is V1. Okay? Analysis is the same. Formula all the same. What's the difference? Huh? What's the difference? No difference. Okay? While theoretically there's no difference, alright, normally these type of devices, there are losses. Alright? There are pressure losses due to you squeezing the flow and all that. Alright? So normally the losses here are relatively small. Alright? Okay? The losses here are relatively large. Therefore, if you were to use this device and you wanted the accurate measurement, you will need to calibrate it and come out with something called a discharge coefficient. Alright? Before I talk about discharge coefficient, there's an in-between sort of arrangement. I think it's called a nozzle or vein or something. To try to help, alright, in between the two devices, you still want to keep the cost down, but you want to get a bit better performance. Alright? Sometimes instead of having just a sharp hole, okay, they have like a small nozzle. Okay? So a small nozzle to guide the flow like that. Alright? A small guide vein or nozzle. Alright? So it's like a cylindrical trumpet. Alright? To guide the flow so that you don't get so much losses. Alright? It works a little bit, it's better, but it's not that fantastic. Okay? And then this is your point 2, this is your point 1. Okay? It costs more than the orifice plate, but less than the Venturi tube, and its performance is also better than the orifice plate, but not as good as the Venturi tube. Alright? So it's an in-between kind of solution. Alright? With some guide vanes. Alright. So, finally, alright, yes. So, there's this thing called CQ, alright, which is called the discharge coefficient. Okay? Alright? So, the discharge coefficient is actually the Q ideal. So, Q actual over Q ideal. So, these devices would tend to over-predict the flow rate. Why? Because, let's say here, alright, so CQ will be less than 1. You tend to actual will be less than the ideal. Ideal, the Q ideal is, this one is calculated. This one comes from calculated using Bernoulli and pressure measurements. Alright, so you take the pressure measurements and then you calculate what it is. That is the ideal flow rate. Alright, that one it should be lah. Okay, but the actual is less than that. Why? Why is the actual less than that? Alright, because, alright, we are assuming here that we are assuming that here there's a pressure drop, isn't it? From P1 to P2, we are assuming a pressure drop. Alright, we are assuming that pressure drop comes solely from where? Solely from where? I assume that pressure drops come solely from the change in velocity. But some of that pressure drop actually comes from losses within the system. Alright? Within either the Venturi tube or the orifice plate. Okay? Because of that losses, alright, the actual pressure drop due to the change in velocity is less. And therefore the flow rate is actually less than what is predicted. Is that alright? Okay? So, because the pressure drop that we measured is overestimated, because it includes the pressure drop due to change in velocity and the pressure drop due to losses. So, but the Bernoulli equation only accounts for the pressure drop due to change in velocity. Okay. So finally, I want to show you. Hopefully it's around. Hopefully it's somewhere here. Okay. So this from the lecture slides. Alright. This is the discharge coefficient as a function of Reynolds number. Alright. Reynolds number. we'll do more about Reynolds number in the next chapter. But for now, Reynolds number is just a dimensionless parameter. Density times the velocity and diameter over mu. Mu is the fluid viscosity, fluid dynamic viscosity. V is the velocity in the main pipe. Not in the hole, in the main pipe, rho and D. Alright, you can see for the Venturi tube, alright, settle down please, last point I'm making today. Alright, for the Venturi tube, the discharge coefficient is nearly 1. So there's very little losses, 0.94 to 1. Alright, the other one, okay, you can see, depending on your diameter ratio, D over D, small d over big D. Okay? Your losses are actually quite big. Your discharge coefficient is very low. Which means a big difference between the actual and the ideal flow rate. See here it's about 0.6. Okay? And the other one is somewhere in between. Okay? You get some nozzle discharge. Okay? I think that's it. Alright. So, with that, I was not able to completely explain the lab part, so I'll do that on tomorrow. Okay, together with this one, I'll have to do tomorrow. Okay, so safe. Alright, those who want my signature, please wait for me outside. Let the next class come in. I think there's a class coming in.